We are now going to simulate quite a different kind of material, which is a permanent magnet. And this is a material called as alnico, made of aluminum, nickel and cobalt. So what we are going to do is we are going to use finite element method, and I'm going to ask a student of mine to simulate this using finite element method to see the magnetic field. In this case we are going to do B field. So we are going to simulate what the B field is going to be. Not only that, if you are going to have an iron rod which is going to be next to it, what is going to be the force of this magnetic field? So we are taking only one magnet, we are not going to do two magnets. So we are going to see and simulate the force exerted by this particular magnet on an iron rod. So that's going to be the first experiment. So the next experiment what we are going to do is a monopole antenna. So this is the monopole antenna, and this is designed by IIT Bombay. So we are going to simulate this antenna, and this antenna is going to operate at 1.25 gigahertz, and as you can see it has a coaxial feed, and it's going to have a kind of ground plane, and we are going to simulate this particular antenna also using finite element method. So let's go and see what the student of mine is going to do and how he is doing this particular model on a finite element method. Aviraj, so you've been working on the finite element method. So could you please explain us how you have modeled this permanent magnet using the finite element simulation? And later on also we would like to see how we have done this monopole antenna. So let's start with the permanent magnet example.
Okay, so what permanent magnets are like physically, what we can say is they are like ferromagnetic materials of iron or steel usually.
Yep.
And they also have basically what we have learned in our physics, in our 11th,
Basic
12th
courses, yeah.
basic courses. So they have a north pole and a south pole,
Yep.
which have the flux lines from north to south pole.
Okay.
Right. So what magnets we have here is alnico magnets who have length of some 73 mm,
Okay.
width of 12 mm and height of 8 mm.
So this is basically for this particular
Yeah.
magnet, you have taken the length,
Length
which
as
is the
this,
actual length,
yeah.
73 mm, and
And
width
the width
is
is
the
this.
12 mm, and then the height is 8 mm. Okay.
So to basically model this physical problem into the software, the FM software, what we'll need is first the block. We'll make a block, model a block
Okay.
of this magnet,
Okay.
of this exact size, and we'll give an inherent magnetization to it.
Okay. So basically, you take the equation B equal to mu H plus M.
Yeah.
So you are giving an inherent magnetization into it. Okay.
Block. So the entire physically what we have is this magnet is surrounded by air.
Yeah.
So that infinite space we cannot model in the software. So what we'll be doing is we'll be closing it in a bounded box of air.
Okay.
And as there is no current involved in it,
Yeah.
so the magnet itself is giving the magnetic field.
Yeah.
So what the solver will be doing is actually solving the scalar magnetic potential.
Okay. So basically, you will be doing with the case of scalar magnetic potential.
Scalar magnetic potential. So the simulation tool.
Yes. Yeah. So go on. So basically, you are starting to do the entire problem using a finite element solver, and you are modeling the thing with the scalar magnetic field.
Yes.
Okay.
So H bar is basically
The gradient of scalar magnetic
potential,
field.
not the J bar plus D bar,
Exactly.
gamma by gamma,
Okay.
K of D bar.
Yeah.
And del dot D bar is 0. So these
Okay.
are the main equations.
Okay.
Using which we will be plotting the magnetic field.
Okay.
So starting with the building the geometry, first we build the geometry. This is the magnet.
Yeah. So this is the basic geometry you are using,
For the magnet.
and the finite element solver you are using basically gives you the kind of geometry that
Yeah.
you have modeled, and you have taken basically the same dimension
Same
from the
exact
physical
dimensions.
magnet you have,
Yeah.
and now you are going to mesh it.
Yes. Before that, we'll be enclosing it in a air box. So
Okay.
a big air box.
Okay.
So that this is my magnet, and I surrounded it with an
So
air
can you
box.
zoom it a little bit for us to see how the entire thing is looking? So this is the magnet that is there, and then the air box is surrounding the magnet. Now,
Then also we are putting an iron rod to see what the force will be applied to that iron rod. So
okay, excellent.
that iron rod is this, if you can see.
So this is the iron rod that we are having. Okay. So if you can show this one. So basically what you have is the magnet, which is here,
Yes.
and then you have a perpendicular iron rod. In
Iron
this
rod.
case, it's just another magnet,
Yeah.
but we can imagine that if this is an iron rod, this is perpendicularly sitting like this.
Yeah, exactly.
Okay. Now we are seeing what is the force of this particular magnetic field on this particular iron bond.
Yes.
Okay.
So assigning the material.
Yeah.
So we'll assign air.
Air for the surrounding
The
space.
surrounding space.
Okay.
And also the magnet, because what we are doing is we are giving some equations of magnetization in the physics itself
Okay.
of the software. So we don't need to put some material, that Alnico material.
Yeah, yeah.
We'll put it as air only, but
Yeah.
the equation which it will be solved, that will be putting as something in the physics.
Okay.
That I'll show you in the next thing. So I put iron in the front.
So this is the iron, which is the material that you have. And for the magnet itself, you are going to do it in a different way.
Yeah. So this is the physics, magnetic fields with no current.
Okay.
So if we go in this and include all the domains, we can see the two equations which I was talking.
So you have the H field that is equal to minus gradient of the scalar magnetic field, and then the divergence of B equal to 0. Okay.
So normally in magnetic flux conservation,
So you are taking the conservation of the magnetic flux, and then
so in the air box,
so whatever flux is going out comes back. So
Yeah.
that's the idea what you are putting in.
so and all the boundaries
Boundaries
will be insulated, magnetic insulator, so
Okay.
that no flux will escape. So it is a bounded medium. So
Okay.
n dot B is equal to 0. That is
Okay.
the boundary condition.
So basically what you're forcing is the normal component of the
Yeah.
B field is equal to 0.
0.
So that means no normal component of the B field means no flux is going out.
Yeah.
Okay.
So initial values in the entire domain, the magnetic scalar potential is 0 in the
Yeah.
entire domain.
Okay.
And here we are modeling the magnetic flux conservation 2.
Yeah.
So here if you can see, B is replaced by mu 0 H plus mu 0 M,
Okay.
and that M I can give here.
So basically what you do is you have the value that you're computing H equal to minus gradient of scalar vector potential, scalar magnetic potential, and then you have the divergence of B, for which you are substituting mu naught H plus mu naught M equal to 0, and then you're computing the value of M from there, and then you're substituting the M value here.
Yeah.
Okay.
So this M will be substituted here, and if we substitute this grad Vm here, so by this single equation we'll get the value of Vm
Okay.
at each point, and by that we can get H
Okay.
in the whole domain.
Okay.
So this is for permanent magnets. If this constitutes a relation, if there is another material, suppose there is some linear material, so we can give relative permeability. So its relative permeability
Okay.
will be given B is equal to mu 0 mu r H.
Okay. In this case, we have taken air, so we are not talking
Yeah.
about the relative permittivity.
Yeah. So there are many other options.
Okay.
Then I have to calculate.
The force
Force in the
exerted
iron.
on the particular iron rod using this magnet.
So
Okay.
I have included a node in this force
Yeah.
calculation.
Okay.
In that I have included this domain, just the iron domain.
Okay. So the force equation itself is
Is the integral of a surface tensor.
Okay.
So by that, the integration in that domain, we get the force in that entire domain.
So this is possible within the solver to
Yeah.
get the value of F.
Yes.
Okay.
So these are all the settings that we have to do, and then the meshing. So what this solver gives is inbuilt physics controlled meshing. So
Okay.
it gives different options of finer and finer
Okay.
meshing.
Okay.
So what is the thumb rule is that means by experimentally or iteratively we can do is
Yeah.
we can go finer and finer
Yeah.
till the results of two settings come same,
Okay.
and the larger setting we can
Okay.
Take
So
it
that's
as
the
a-
convergent aspect
Yeah.
what you're looking at.
Yeah.
So can we see the results?
Yeah.
So this is giving you the magnetic field B for different planes.
Yes.
Okay.
I have just plotted this in a single plane.
Okay.
We can see it in 3D also.
So this is basically one plane,
plane.
which is basically sitting on this particular surface.
Yeah. This surface.
Okay. So basically you've taken this surface
Yeah.
and then you've calculated the magnetic flux. So it
Magnetic
goes from the north
Hmm.
to south. So basically it goes
It's
from,
diverging away and it's coming
Okay.
here.
and the force value, how can
Okay.
we
The
compute?
force value, it gives a number global evaluation. Here we can give some expressions. There are some inbuilt expressions, lots of things we can calculate. So what I have done is
Okay.
magnetic field, no current, force,
Yeah.
and evaluate. So 0.06 newtons
Okay.
is the force exerted on that
Particular
ion.
So that is the force that is exerted by this particular magnet on the bar of iron that
Yes.
we have, and this is 0.06
Newtons.
newtons. So it's going to depend on the magnetic field of the material
Yes.
itself, and
The
also
distance.
the distance between them.
Yes.
Excellent. So this is a good example for us to see how you can use a finite element to understand and model permanent magnets.
Yeah.
So I know that I asked you to also look at the monopole antenna, which is operating at 1.25 gigahertz. So if you can explain us how you model this monopole antenna in the finite element solver, it will help us to get a sense of what the things that we need to know about modeling such antennas and finite element based methods. So this is a simulation for monopole antenna, okay, and you are starting with the basic model what we have in our hand.
Yeah.
Okay, and so explain us about a little bit about this antenna.
So this is a basic monopole antenna, which is of length lambda by 4.
Okay.
So whatever frequency, this is designed at 1.25 gigahertz. So the lambda at 1.25 gigahertz, we basically divide it by 4 and take the length.
Okay.
And this is the reflector plate.
Okay.
So ideally, what people do is ideally the monopole antenna should have an infinite plane, but
Okay.
that is not possible practically.
Okay.
So it's like a finite plane here. So this.
So what it acts as a reflector plane, as
Yeah.
in this is also having certain role in directing the beam of the
directing the
antenna.
beam, yeah.
Okay.
So
It's a very similar case in the case of a patch antenna where you have a ground plane,
yeah, exactly.
which also acts as a reflector.
Yeah.
So in this case, you don't have any dielectric in between, but you have a reflector plane
Reflector
which
plane.
acts as a ground plane or a reflector plane. So explain us how we have gone from this physical model to the next step.
Yeah, so basically this was the antenna, and virtually what will happen is again this will bring an issue of physically it has a air surrounding it, and it should
So
be
we
a
have to
infinite
confine it.
plane. Yeah, so we have to confine it with something. So here we have used the perfectly matched layers.
And what is the discretization you are using?
Discretization is again in this particular frequency problems, it's like the thumb rule is lambda by 5.
Okay. Okay.
So the element size should be lambda by 5
Okay.
or less.
And what I also see that is the input impedance of this particular antenna is
Is
32.5
plus J 21.5.
Okay, so it is a complex impedance
impedance.
where you have 32.5 as the real part, and then the imaginary part is 21.5.
Yeah, so that's what the issue is, that the feeding cable which we use, the coaxial cable, has some real impedance, maybe of 50 ohms or 75
Yeah,
ohms.
yeah.
So there is an inherent mismatch,
Okay.
little mismatch in the
In the antenna itself. So the feeding cable is normally in the range of 50 ohms. Okay.
So again, in this simulation, this type of simulation we solve is the wave equation.
Okay.
So by this wave equation, we find the electric fields at all the points in the domain.
Yeah.
So we can go to.
So basically, what you have is a wave equation.
Yeah.
It's a curl formulation,
Yes.
and it's totally in terms of E.
E.
And what we have is the relative permeability, and you have the sigma, which is the conductance, and then omega and epsilon naught. Okay, and k naught is the wave number.
Yeah.
Free space wave number. Okay. So you're basically modeling this particular geometry using the finite element solver.
Yes. So this is the domain is entirely enclosed with this
PML. Perfectly
so
matched.
I have hidden this things just to show you.
Okay.
The inside part.
So what you have got here is basically the domain and its internal geometry. What we see here is a reflector plane here, and you have a lambda by 4 monopole which is there.
So practically, to compensate for the capacitance, there is an inherent capacitance in the design. So for practically, what we do is we reduce it slightly by lambda by 4. It's not exactly lambda by 4.
Okay.
It's like small length is reduced by
less than lambda by 4. Okay.
So after building all the geometry, what we do is assign materials.
Okay. So here inside is air.
Inside is air, and then all the things are metallic.
So you use copper as the base material.
So
okay. and then
this and this.
and then you have a
Teflon for the field.
So the field
coaxial
area here,
coat.
so where you are using Teflon material, so as to insulate between the reflector plane and the actual monopole.
Exactly.
Okay.
So here what we are using is electromagnetic waves physics.
Yeah.
So in this, what I have showed in the slide, this is the equation which we
So
saw.
you have a curl formulation, and you get a wave equation in terms of E.
So in this electric waves physics, what happens is that by default PEC is used as a boundary in the entire domain.
Yeah.
So which gives n cross E.
So the tangential component of the electric field is set to 0. Okay. And this is again you're done in the frequency domain. You're solving this in frequency domain. What is the frequency you're operating? It's 1.25 gigahertz. Okay.
Yes.
So let's see the kind of initial values.
Initial values are 0.
Yeah.
Everywhere. And then what we include here is we include far field domain because we want to calculate the far fields of the antenna.
Okay.
Now how to field is here is the coaxial port, the lump port.
Yeah. Can you zoom this one to show us how the coaxial field is looking like? So this is basically this part where we have the coaxial field coming.
So this is the inner conductor.
Yeah.
And that is the outer conductor, and between that is the Teflon.
Yeah.
And we have just given the excitation to that part.
Okay.
So the waves will travel in that, signal will travel in that part.
Okay. So this is the coaxial feed what you're having?
Yes. So what we are given is the coaxial feed to this part itself, and we have excited it, wave excitation, and this port is on.
Okay.
So the next step is meshing.
Okay.
So again we have used the physics control mesh.
Okay.
And again what I had told, we can go fine and finer.
Okay. So you are talking about roughly 5 lambdas, 5 cells per lambda.
Yeah, exactly.
Okay.
So here the frequency domain studies, I have given the 1.25 gigahertz.
Okay.
And after simulating, what we get is such kind of far fields.
So basically what you see here is the reflector plane is here, and it's kind of reflecting the entire thing. So what you're plotting here is the E field, and then the reflector plane is pushing everything on the upside. Like
so without the ground plane, what it will be?
It will be like an apple.
Yeah.
It will be
so the
apple.
maximum will be here.
Yeah.
So the maximum is a bit shifted upwards.
Okay.
So here where 0 is there's the ground plane, and the maximum is shifted here.
Yeah.
So what we can see is on the axis there is no radiation.
Okay.
And
so this is classically like an apple. Okay. So this is the far field value for this particular antenna. So could you please show us the far field value that you've been showing?
Yeah.
So this is the electric field, basically the far field value theta for this particular. Okay. And the theta component here is being shown. And could you please also show us that plot what you had before, the polar plot? So the polar plot is basically the far field value and normalized value. And then you see that it's directed on the upside. So this is the ground plane area. Okay. And this is the electric field. So these are the electric field directions. So basically what you see, can you explain us?
So what you can see here is like the electric fields are going outwards from the antenna.
Yeah. So and it's getting pushed up by the reflector plane.
So there are less electric field vectors below the plane and more above the plane.
And that's the main purpose of this particular kind of reflector plane, is to push the radiation more or less in the upside. Okay. So how long did you take to simulate it? Roughly modeling this kind of antennas is for a design engineering point of view. Once we have the dimension and once we have the right aspect of the frequency that we are interested in, modeling this is, since it's a frequency domain, it doesn't take a long time.
No, not long.
But what if I'm interested in doing a broadband simulation?
So for broadband simulation, I think the geometry itself has to be a bit modified.
Okay.
So that is like a research topic. So
okay. So this is kind of a focus for antenna engineers to think into. From the numerical point of view, so can you also do a similar design using finite element time domain method, where you can basically send in a Gaussian pulse and then you can see a broadband aspect?
Yes. Okay. We can see that.
Okay. So that's something that you should try in the next example. But I think for now, it's a good thing to know how you can simulate any kind of antennas using finite element method. Particularly, we looked at the monopole antenna, where we see how the radiation pattern is going to look like, what are the ways in which one can model it. So we also looked at much of the important aspect of modeling itself, because one thing is to have a physical antenna, the other one is to make them, model them in a virtual platform. So there, the question of how you're truncating the thing is coming, and things are there. So what are the other methods you normally do in modeling this kind of antennas?
What we can do is like we can do this similar thing in CST, which uses the
So this is
FID.
basically, you can also model it using a finite integration technique or finite difference technique. And then it will be a time domain broadband approach.
So what you said, the Gaussian pulse excitation and all is done in CST. And also one other thing we can say is we can also apply the scattering boundary condition in this solver. But the scattering boundary conditions need the normal incidence of the wave. So that gives a bit higher reflection than the perfectly matched layers.
Okay, so perfectly matched layer solves the problem of reflection issues. Okay, so excellent. So thanks a lot, Aviraj, for showing us two problems. One is using a permanent magnet, and the other one is using a monopole antenna. So both of them we have tried to look at kind of a finite element solver, where we can model such practical problems and then get certain practical results, so that we can either improve the design of certain antennas, improve the directivity of the antennas. We're also looking at magnets, what are the strengths, and what is the pole strength and things of that sort. So thanks a lot.
Thank you.